I'm going to talk about data analytics for climate decision making. This is actually the front cover of the Ladybird book that Ian mentioned that I've authored with Tony Juniper and Prince of Wales. And in a way, it highlights why it is absolutely critical for us to try to improve our information that can be used to try to help make decisions, not least in terms of building robustness of infrastructure and other planning decisions associated with climate change. In the UK, we've seen a series of flooding events over recent years. This particular picture was inspired by the floods that we had in autumn 2000, that in particular affected villages like Upfield. And it's clear that at least some of the floods that we've seen in recent years, the risk of those floods occurring has been exacerbated by the climate change that we've already seen to date. And in part, that's simply because a warmer atmosphere holds more water that can be then rained down in heavy rainfall. So I want to start off just by giving a bit of an overview of the financial and human costs of extreme weather, just to motivate in a little bit more detail why we might want to be going about trying to provide more robust information to try and help decisions that we'll be taking now and over the coming years and decades associated with building resilience to weather and climate. So here are two particular examples. Top is Hurricane Sandy, an example of a very severe weather event that hit particularly in the United States in 2012. And one of the biggest impacts of that came through the flooding that occurred in the associated storm surge. And you might recall that that caused particular damage to the subway system in New York, and indeed the damage from that is still being dealt with today. And Line L, which is one of the major subway lines in New York, is due to close for 18 months next year in order to try to repair the damage that was done during this flooding. And if we look overall at the financial and human cost of this one event, just within the United States, more than 100 people died as a consequence of this severe storm, and the financial cost runs into tens of billions of dollars. Bottom is a different example. This again is an example of flooding in the UK. This was in 2007, and what you're seeing is a picture of an electricity substation just outside of Gloucester. They came very close to being taken offline as a result of that flooding. That electricity substation provides electricity for more than 500,000 homes, and apparently GCHQ. Well, I suspect GCHQ's got a backup generator on. But it also provided power to a sewage treatment facility and various other critical infrastructure. And it was estimated that if it had gone offline, it would have been at least 3 weeks before it had been able to be put back online again. So it's one example of the interconnectedness of the risks that can be posed by extreme weather events. Another example that I wanted to give, back in 2015, we had a severe heat wave. We've actually had a series of severe heat waves in this country as well, 2003, 2010, and then in 2015. This was the Telegraph from the 29th of June. Those of you who are from Cambridge will recognise Dalton College pictured there, which is actually my college. And it warned of temperatures reaching 35 degrees centigrade on Wednesday of that week. I know this particularly well because this was me at the time. And so on the Wednesday, when it was severely hot in Cambridge, I got dehydrated and ended up down at the Rosie Birth Centre. And Eloise, who you can now see sitting over there, was born a few hours later in rather more dramatic circumstances than I might have thought, because I was severely dehydrated. And it's an example of the health impacts that are associated with these severe heatwave events, particularly affecting people who are pregnant, but also the elderly. And there was a severe heatwave in Europe in 2003, and it's estimated that across Europe, 70,000 people died prematurely as a result of those extreme temperatures. And again, the evidence suggests that climate change that we've already seen to date has increased the risk of those sort of events occurring. Just a couple of weeks ago, the latest climate change risk assessment for the United Kingdom was released by government, and these are the top 6 risks that are deemed to be the ones that the UK must be most concerned with now and over the coming decades. Flooding, high temperatures, these sort of extreme heat waves that I've been talking about, risks to water supply, risks generally to natural capital, biodiversity, ecosystems in the country, risks both domestically and internationally to food production and trade, and risks associated with new and emerging pests and diseases. Now I want to talk a little bit about the challenges around quantifying climate risk. So if we understand that there are a range of different potential risks facing us in the UK and internationally associated with climate change, how can we go about quantifying exactly what those risks are and then put in place planning associated? So the traditional approach to doing this is to use climate models. If you're talking about projections into the future, then we're reliant on using computer simulations of that future. And there are sophisticated models of climate based on the sort of models that are used to forecast the weather that can be used to project climate into the future. And then combine those climate models with which provide information on what various aspects of the weather might be like, or meteorological variables might be like into the future. Combine those then with some sort of model that says how that relates to whatever process that you're ultimately wanting to make a decision around, whether that's something to do with water resources, or food security, or infrastructure resilience. Now, there are a number of challenges associated with that approach. So the first challenge that I want to highlight is that the raw output of climate models has a number of issues itself associated with it. So what you see there in the picture up there is some actual output from climate models. The first thing you can see is that climate models only have a certain resolution. You can see some of them are at lower resolution than others. And if you're wanting local detailed information, that's simply not available in those kind of models. They average over quite large areas of many tens of kilometres. It's also the case that many of the climate models have systematic biases, particularly at a local scale. So you can see here 4 different climate models, and they're each showing slightly different projections out to the future. And if you compare them with observations, in fact, actually, what's shown up here is 3 climate models and observations on the top left, then you can see certain places where the climate models, so these 3 here, are showing something different to the observations. And in particular, if you look here in the Alps, the observations should show cooler temperatures, shown by this blue over the Alps, and that's just simply not really picked up in the climate models. So there can be systematic biases. The next issue associated with this is if we're talking about projections through to the future, climate model projections are based around climate model projections are based around inputs that are some sort of scenario of what our future world might look like in terms of, in particular, the amount of emissions of greenhouse gases that we'll make to the future. We don't know what pathway we're going to follow in terms of future emissions. It might be, here's an example, of looking at future temperature under different scenarios. This is a scenario where we reduce our greenhouse gas emissions quite substantially, and the temperature increase is rather limited. This is a more business as usual. We do nothing particularly to reduce our greenhouse gases, and that's the temperature out into the future. But there's a significant amount of uncertainty, a range of values for these projections based around, firstly, what we might be doing in terms of our future emissions of greenhouse gases, but then also uncertainty because of the differences between different climate models, and also just the chaoticness, the variability within the climate system. Now you add on to that sort of range here of values for the weather-related variables coming from the climate models. You then, if you're wanting to actually look at some end decision, perhaps to do with crops, you've got further uncertainty that's associated with how those weather variables then impact, say, the growth of a particular crop. And as you go through this process, you get a ballooning of uncertainties. There's a big range of uncertainties on the weather variables, and then an even bigger range of uncertainties when you then look at the end quantity that you're trying to forecast. Now, it seems that most things these days, debates these days happen over Twitter. So earlier this week on Twitter, I was told that this book that I've Ladybird book that I've written, there were emissions in the book which were simply dishonest, said an economist, Richard Tom. And in particular, he accused us of having omitted to include what he described as effects that are and remain positive, such as winter heating and winter mortality. Okay, so we include lots of things. You're welcome to look at the book. I've got a copy here, if you want to look at it after the lecture. Lots of things that we do talk about. And actually, it's important when we're thinking about climate risks to understand what the things that we are confident about and what the things that scientists were less confident about. So there are some things in terms of risks that we are very confident about, reasons to be particularly concerned. And there are two that I've highlighted here that are mentioned in the book. First is looking at certain particularly critical habitats, for example, coral reefs, where we know that even rather modest increases in temperature are threatening those coral reefs. Actually, also combined with another effect of increasing carbon dioxide in the atmosphere, which is acidification of the oceans, which are impacting those coral reefs. Another cause for concern is indicated here, which is in terms of the potential for very large-scale changes to the climate system. And one example of that would be the melting of the ice sheet on Greenland. We know that in the past, as indicated in this figure here, there's been much less ice on Greenland, and in particular when temperatures have been not much warmer than they are today. If the whole of the Greenland ice sheet melted, that would lead to many, many meters of sea level rise. So that's a significant cause of concern. In terms of some of the other impacts of climate change, we're less confident in terms of the science. So, for example, if we look at crops, as we describe in the book, there are certain crops that may actually benefit from modest increases in temperature. But when we look at the world as a whole, we see continued climate disruption, and as the world as a whole, we're likely to see less secure food supplies. Now, what about winter heating and winter mortality? Well, this is an area which is more complex. So I picked this up off the NHS website. We're very familiar with the fact that the NHS tends to have a crisis every winter. We're in the midst of one allegedly yet again. The NHS has a stay warm and well this winter campaign going on, and food poverty is a very real challenge. But it's an interesting question to try and understand the relationship between weather and health outcomes, particularly in terms of cold weather. So there are two aspects that one would need to really get to grips with in order to make robust projections associated with that. The first is to understand what the climate impacts of winter weather in the UK are, and the second is to understand how winter weather, cold temperatures in particular, affect health And I would suggest that we don't know robustly either of those at the moment. So at the top here, I've got an example. In fact, actually, my PhD student, Christine, is sitting here in the audience, and this is her work. This is looking at the impact of reducing sea ice in different parts of the Arctic Ocean on temperatures throughout the rest of the northern hemisphere. And so the critical thing that there's two different places in which Christine has modelled reducing sea ice, first in the Barents-Kara Sea, and secondly in the Chukchi-Bering Seas. And you can see that between these two, this is what you're seeing is the impact on temperature, and you get quite different impacts on temperature according to exactly where in the Arctic the sea ice decreases. But most importantly, if you look at this case here, when the sea ice has decreased in the Chukchi-Bering Sea, although the temperatures locally increase, the impact ends up having a statistically significant decrease in temperatures in the UK. Now, this is a very idealised model, but nevertheless, it shows that the pattern of change that we might expect under future climate change is not necessarily simply a warming of temperatures everywhere. You can actually have impacts that lead to cooler temperatures in some locations. And then, actually, the impact, the health outcome associated with temperature is also not as clear-cut as it might at first seem. So this is a recent study that looked at a range of French and American cities and looked to see the effect of temperature on mortality figures. And what they found was actually that there's rather little difference between cities that are in very different locations and very different temperatures in terms of their mortality figures, suggesting that actually winter temperatures are not that significant on their own in terms of health outcomes. And indeed, these plots, the slide here, show temperature change and increase in mortality in Paris and in New York. And what you see is that actually there's a much greater increase in mortality risk at higher temperatures than there are at lower temperatures. Indeed, rather little difference in New York. And some of that seems to be, the suggestion is that actually, although many people succumb to flu and other respiratory diseases in winter, actually a bit of an increase in lower temperatures doesn't make a major difference. The fact is there is either flu going around or there isn't, and the temperature per se is not the dominant factor. Now, of course, it's probably more complicated than that, and not least because weather effect on health, particularly associated with respiratory diseases, is almost certainly not just through the temperature, but also through things like the amount of humidity in the atmosphere. So, to try and properly assess the weather dependency of health outcomes, one would need to take into account more than simply temperature. So the bottom line is that as far as I can see, we don't yet have robust protections associated with this, but it's clearly critically important. There's two other things that I wanted to highlight as being real challenges. First is how to account for correlations that we know exist. So one of the key drivers of weather in the United Kingdom is something called the North Atlantic Oscillation, which affects the position of the jet stream, which brings much of our weather from North America to the United Kingdom. And depending whether it's in one state or another, we typically either have rather cool, dry conditions or rather warm, wet conditions. And those are then correlated with other consistent patterns of change in other parts of the world as well. Another example that you might have heard of these correlations between different locations is the El Nino phenomenon, which causes weather impacts throughout the world that are highly correlated. Now, depending on what end system you're interested in, imagine it's something, for example, to do with food, which might be sourced from different regions. If you want to properly understand the system risk associated with food in a global context, you would want to understand the correlations between these impacts in different parts the world. Geographical correlations are one example. Another example would be simply the correlation between different parts of that, say, food system. So here's an example below where there was, again, it's one of the severe flooding events we had in the UK. There's an example here of a potato field that was severely flooded. There have been a number of occasions recently where we've had flooding in autumn, where large percentages of the UK potato crop has been destroyed in the ground overnight as a result of that flooding. But then if you're thinking about the food system as a whole, the fact that some of the distribution facilities and indeed stores were flooded has an impact on the full food system. And these are clearly correlated events. And the final example I wanted to give is that if we're wanting to fully understand the present and future climate risks, we also have to account for non-linear effects, in particular what might be very high impact but low probability events. I've already given the example of the Greenland ice sheet. This is an ice sheet in Antarctica. We know that both in Greenland and in Antarctica, there's the potential for ice sheets to melt and collapse, which could lead to very large-scale impacts. And there are other examples of other parts of the climate system that similarly have the potential to undergo abrupt or irreversible large-scale impacts. Right, finally I want to talk a little bit about new data science approaches. And this work was very much inspired by David Mackay, who many of you may have known, sadly passed away last year, and was famous for two books, Sustainable Energy Without Hot Air, which many of you may have read, but also his work on machine learning, inference, and information theory. And it's the combining these two different interests that led to me having many discussions with David about how we might be able to use data analytics type approaches to try to address some of these real challenges in climate science. So what we've been trying to do is firstly to try and take a more risk-based approach to using some Bayesian principles, using climate models and the outcomes of climate models as in the jargon triers. So the sort of questions that we will be trying to address is what is the risk of temperature exceeding some particular threshold, let's say the 35 degrees centigrade of the heat wave in 2015, at some point in the future, say in the 2030s. The sort of pathway here is to understand the problem and its context, and bring on board all the available existing data sets, whether it's existing data sets of current and historic climate conditions, or data sets of, for example, health outcomes. Combine those together with the climate model projections, downscale the climate model so that we've got local information, remove the systematic biases, and combine this all together to produce a risk assessment. There's an important distinction between taking a risk-based approach and the more traditional approach that I described earlier, which had the potential to succumb to those ballooning of uncertainties. And one of the things here is that we typically, in this risk-based approach, interested in looking at extremes. And when you do that and you're looking at changes in thresholds, you often find a much greater differentiation between different situations than you might do if you were just looking at the average conditions. And here is actually an example where this study looked at the risk of having the sort of very hot summer that we saw in 2003. And so the background risk of having a very hot summer in Europe was something like 1 in 1,000 years, maybe a bit less. By the end of the 20th century, that was down to 1 in 50 years, and today it's estimated to be about 1 in 5 years. So very severe changes in risk when you look at these threshold values. Now in 2015, in August, there was a severe heat wave in Egypt, associated with more than 90 deaths, and it's estimated that the likelihood of having such a heat wave had indeed increased as a result of climate change we've seen to date, and work that we've been doing with Scott Hoskin, who's sitting here in the audience, and the European Bank for Reconstruction and Development, has been to start to look at whether or not we can provide projections into the future to help decisions being made surrounding the future need for air conditioning in Cairo, and then the impact on the Egyptian power network. Now, some of the challenges associated with that, this is data. First of all, these are data from actual observed stations, and then there's some interpolated data shown as well. There are systematic biases in all of this, and we've been looking at ways to try and account for those systematic biases. And then in terms of the future model projections, we're looking at different ways of combining the different future model projections with historic data to try to eliminate the systematic biases in those future projections and downscale the projections to the local area, in this case of Cairo. So what you're seeing here is the observations in 3 climate models showing quite different assessments of what the conditions between 1980 and essentially the present day were. We can use information on the differences between those climate models and the past observations to then help scale future projections, and that's what's been done here under different methods. And what we're interested in trying to do in collaboration with colleagues at Google DeepMind is to try and see whether we can use various different machine learning approaches to try and do that sort of assessment in new and potentially better ways. And here's just an example of the sorts of things that we are interested in doing, but also highlight some of the challenges associated with this. So this is a sort of canonical example that's often used in machine learning. What you're seeing here is the observations of carbon dioxide in Hawaii, the key measurement station that's used to measure global carbon dioxide levels, and you can see this steady increase from 1960 through to the present day, with a seasonal cycle on top of it. So the key characteristics of this time series are that you've got a trend, increasing trend, a seasonal cycle, and then some what you might describe as noise on top of that. And the machine learning approach that one can apply using Gaussian processes is to essentially use this past data to fit the parameters of some predictive method that then allows you to make a prediction out into the future based on this historic time series, using the characteristics of the data itself. Now, the analogy that we would like to use is to similarly, as in cases like this, to use information about the patterns that we see in historic data to then help project into the future. Now, one of the critical things that you can quite easily observe on this carbon dioxide is if we're thinking about projecting into the future, as I've described already, obviously there's a large uncertainty as to what exactly as a global economy we might do in terms of our future emissions of carbon dioxide, and that will clearly impact the future of the measured concentration of carbon dioxide even lower. There are 2 of the standard projections that are shown here. This in red again is the same red that I showed you previously. That's the essentially business as usual future where we do little to reduce our emissions, and in blue is the future where we strongly reduce our emissions of carbon dioxide. Now, those obviously straddle this projection, which is based purely on historic emissions of carbon dioxide. But one can imagine refining this approach such that you combine information that's inherent in the data, historic data, together with information from the future projections. And that's very much what we're wanting to try and explore in these approaches. Can we use both information using machine learning frameworks from the historic data, combine that with climate model projections to come up with a more sophisticated understanding of the future impacts? So that's the goal. The end goal of all this work is to try and find an automated, operational way of producing assessments that may be scalable for many different problems and can provide decision-ready information across a range of different examples that might start off being rather simple, things that might end simply on terms of particular thresholds, temperature, for example, flooding, might extend through to more complex examples where there might be multiple variables. Temperature, water and sun, for example, are all important for crops and understanding future crop yields. To very complex examples that might be something that depends on multiple different locations and multiple different meteorological variables. And one example there, the integrity of the European power system. So there's a very huge hierarchy of different, more complex examples that might be able to be addressed by this subject. That's the goal, and we're just starting off down in this direction. My sense is that we've already made some progress and that there's an awful lot of opportunity